So I'd like to say a little bit about white dwarfs. They kind of get a bad rap. People say they're dead stars. That's really pretty insulting. I like to think of them as retired stars. You know, you wouldn't go to your grandparents and say, Grandma and Grandpa, you're dead. You know, they'd say, come on. And then if you tried to make it good and say, well, actually, you're undead, that still doesn't work very well. So I like to think of them as retired stars. And just like your grandparents, the more you know about them, the more interesting they are. And they get to do new stuff that you know, you never really knew about. So anyway, I'm at the Department of Astronomy just up the road. And it works in everything. So stars are the fundamental building blocks of, I like to say the universe, but certainly galaxies. So all these little blips of light that you see are stars. And you know, you look up in the sky, those are stars. You look at the Milky Way and it looks like white clouds, but it's actually millions of stars so close together, they blend together. So everything is stars. And so in some sense, I like to think of them as like atoms, because atoms are the building blocks of the universe. And stars are like atoms, but of course, it's not exact. So unlike atoms, they're not unchanging because they're born, they burn hydrogen and helium, they run out of fuel, they change size, they change mass. You know, you can have a young star or an old star, but a young atom or an old atom, they're the same. So stars are not the same as atoms, but they kind of are. So of course, our most important star is the sun. And it was born about 4.5 billion years ago out of a gas nebula, dust and gas. And it's been about the same over the last 4.5 billion years. So here we are now. And we've got about another 4.5 billion before it starts to run out of hydrogen in the core. And it swells up and gets really big as a red giant, which is like 100 times larger in radius. And after that point, it'll lose a lot of mass and condense down and go into the retirement stage here and become a white dwarf. And of course, as it does this, there are certain consequences for the Earth. So here's the sun now, and here's the sun on drugs. No, here's the sun now, and this is Mercury's orbit, Venus' orbit, Earth's orbit. And when the sun becomes a red giant, it'll be at least this big. And so it may not engulf Earth, although it might, but it's sure going to make it real warm here. So I brought my son here. He's 7 years old. I won't say exactly where he's sitting to embarrass him. But, you know, we were talking about this, and he said, the Earth will get really hot. What are we going to do? And I said, well, we can always skip out to the outer solar system. Pluto will be kind of a decent temperature at that point. So anyway, you know, we had this conversation, and then I remarked a week or two ago that, you know, global warming is happening, and things are a few degrees warmer, and we're having warmer years than average. And he said, Daddy, is the sun already becoming a red giant? So I was like, pretty good, pretty good. We need to get you on some government panels and stuff. So anyway, the last thing that the stars do after it's a red giant, it loses a lot of mass. And these are pictures of stars losing mass. And boy, are they pretty. In fact, I gave a talk up in Delaware about 3 months ago, and I said, yeah, look at all the different ways stars can lose mass. And I got a question from the audience where they said, well, if they can lose mass in so many different ways, how can you possibly understand that? And I was like, oh, that's very perceptive. We don't understand that very well at all. In fact, we don't know how to model it very well at all. Very good. But what we can do is we can study what happens after they lose all that mass, and that's the white dwarf star. So we study the white dwarfs because we can, and we're going to work on the other stuff later. So a white dwarf, when it's born, it's like the center of a red giant. The outer layers have gone away, and you're left with this hot little nugget, which just cools off with time. And so it's a lot like coffee. If you imagine brewing a pot of coffee, it gets really hot, and then the coffee maker goes off. And if you take it out and set it on the table, it cools off with time. And eventually, after an hour, it reaches room temperature. Well, if you put a thermometer in it, and you came back after 30 minutes and you say, oh, well, it's cooled down to 110 degrees, then you could work backwards because you're a whiz at modeling how fast coffee cools off. And you could say, oh, well, somebody took that out of the coffee maker 10 minutes ago. So you could use the temperature of the coffee to figure out how old it was. Well, we can do the same thing with white dwarf stars, except instead of time being in an hour, it's more like 10 billion years. So here's a white dwarf, and when it's born, it's real hot, and it just cools off with time. And so as it gets older and older, it gets cooler and cooler. So if we go and measure its temperature, we can figure out how old it was. Now, in the late 80s, there was a little bit of a paradox with this because we'd done this for a bunch of stars, and we found out, well, there aren't any white dwarfs any cooler than 4,000 degrees. There aren't any 3,000 degree ones. There aren't any 2,000 degree ones. Now, some people thought, well, our instruments aren't sensitive enough to see them, but we actually knew that they were. And it turns out, Don Winget at UT Austin had the brilliant idea, there aren't any white dwarfs cooler than that because the universe isn't old enough for them to have cooled off that far. And people were like, whoa, that's a big thought, you know? That's a really big deal. And so back then, we worked out that our galaxy, the disk of our galaxy, was only about 10 billion years old. And at the time, we really didn't know how old the universe was. Some people said 15 billion years, some said 20, some said 25. So coming along and saying that our galaxy was only 10 billion years old was kind of a big deal. And it's turned out that the age of the universe that we thought it was has come down from 20 billion years down to about 13.7. But the white dwarf age in the last 30 years hasn't changed at all. So we feel pretty good that we can model these stars and use them as chronometers. And they're pretty darn reliable. So yeah, now we think our galaxy, the disk, is about 10 billion years old. Other parts are about 12 billion, and the whole universe is like 13. So one entertaining, again, like your grandparents, you know, you go and you find out that grandma has this weird hobby you never knew of. You know, maybe Texas Hold'em. You know, maybe something to do with beads. Maybe something really crazy that only some other person in the Ukraine is doing. Well, white dwarf stars, as they cool off in their insides, they actually crystallize. So they've got a bunch of carbon atoms, oxygen too, and they're running around, and they're positively charged. They push on each other, and as they cool off, they start moving slower. So imagine that's the center of a white dwarf, all little atoms running around real fast. But as they cool off, they can't quite push their way past each other anymore, and they start to settle into patterns. And if you watch the pattern develop, it starts to become more regular. Yeah, somebody said lattice. Yeah, it's a crystal lattice that's forming. So as these stars cool off, they actually crystallize in their core. Oops, it's happening again. So, so actually we did this research about 15 years ago, and a collaborator of mine released it right before Valentine's Day. And so of course the spin was, well, this is the largest diamond in the sky. Because if you crystallize carbon, then it's, you know, a diamond, which is cool. I mean, I'm all about promoting science and everything. But I happened to be in Cambridge at the time, and I was interviewed by the BBC on the radio. And so their science correspondent's pretty sharp. And he looked at me and he said, so this isn't exactly like a diamond on the Earth, is it? And I said, well, not exactly. Because I didn't want to make everybody depressed. But it is crystallized carbon. But if you took it out, you know, it's like spring-loaded. It would just explode. It's not like a diamond on the Earth. So anyway, another bizarre hobby that white dwarfs have is they pulsate. So, and imagine that's cool and blue is hot. And so this is dimmer, hotter, dimmer, hotter. And as these patterns go across the sky, it gets, across the star, it gets brighter in total and dimmer in total. So we're too far away to see this pattern on the surface, but we can see the total brightness of the star going up and down. And it can do it in different patterns. And there's actually a precedent for this, and it turns out that these pulsations tell us about the inside of the star, the frequencies and the periods that they can do it at. It sort of really is the music of the spheres. It's slowed down a lot, but it really is the music of the spheres. We can do this. Why does this help? Well, consider seismology on the Earth. So here's a picture. I should have cited Wikipedia here. Sorry about that. So here's an Earth. here's the Earth, and imagine an earthquake here, and this is sort of showing how the waves might travel through the Earth. So imagine an earthquake here. It sends out waves in all directions, but if you have a detector here, one wave will go there, and another wave will go here and here, and it turns out that this is how we know about the inside of the Earth. If it weren't for earthquakes, we'd know pretty much nothing about the Earth. We know that it has a solid mantle, mostly solid, but it has a liquid core. We'd never know the Earth has a liquid core without seismology. So almost all of our knowledge of the Earth's interior comes from seismology. Well, there's a field called helioseismology, which isn't earthquakes on the sun, but think of them as continuous earthquakes. It's the sun pulsating in a bunch of different modes all at once, and each one tells us something slightly different about its interior. And they're really low amplitude, but we can see it really well because we're close to the sun. And the sun actually has millions of pulsation modes. And each one tells us something different. So we actually know more about the interior of the sun than we do the Earth, which is pretty cool. So now white dwarfs pulsate, not in millions of modes, but in dozens of modes. And so we're actually able to learn about their interior structure too. And here I've just made another movie of what I think the surface looks like. What we really observe at the telescope is the light curve going brighter and dimmer, brighter and dimmer. This is about 3 hours of data, so I've sped it up by about a factor of 100. And you might say, wow, that's really dull. You're just sitting there in the dome, taking the data, and it's really slow, like the world's slowest video game. But actually, if you're an astronomer, it's super exciting. I don't have to wait for millions of years for the star to decide to do something. It's doing it in 10 minutes. The time it takes to go up here and down is like 15 minutes. And so you can't help yourself when you see it getting 30 or 40% brighter thinking, maybe it's going to explode this time. So, but it is really cool, at least if you're the right personality for it. So we still have problems though. We don't know everything about white dwarfs. We know that they're mainly carbon and oxygen from the pulsations. We know that they have a tiny thin layer of hydrogen on the surface, kind of like the ocean on the Earth. And they've got a little bit of helium too. But we don't know their masses perfectly. In fact, different techniques give us different masses up to 30% different. So imagine you went to the doctor, and you said, "Doctor, how massive am I?" And in my case, the doctor would say, "Well, you're about 200 pounds. But there's a 30% error, so you might be 260 or you might be 140. And I don't know what most of you would say, but I would say, I'm going to go see a different doctor. So we really should be doing better than this. It also, their masses depend on how fast they cool off, so we really care about getting that right. So the main way we get masses for white dwarfs is we look at their spectra. So what's a spectrum? A spectrum is like all the light in the different colors. And, when we look at a traditional rainbow, it's continuous. But when you look at something coming right from a star, it's got these black lines in it because the atoms in the surface of the star absorb some of the light. And hydrogen atoms might absorb this line and this line. And it turns out in stars, and in white dwarfs in particular, the more massive they are, the higher their gravity is, the broader these lines are. You see this is a wide black line and this is a narrow one. Well, if this white dwarf had even more mass, this line would be twice as wide. So we use how wide the lines are to figure out how massive they are. But our theory to do that isn't quite right. So we need a way of doing this that doesn't depend on the theory so that we can make measurements in the lab. In other words, let's produce a spectrum in the lab, make it a certain temperature and density, and measure how broad the lines are. So in order to do that, we've gone to the Z machine at Sandia National Laboratories. This is called laboratory astrophysics, and it just sounds so cool when you say laboratory astrophysics. So what the Z machine is it's a pulse power machine. This is about 2/3 the size of a football field, and it stores up power and releases it all at once. You can't see it, but there's a giant tank here of oil and another one of water, and embedded in that tank are huge capacitors. If you look in electronics, capacitors like this big. These capacitors are the size of refrigerators, and there's 36 of them arrayed around there. When they want to repair something, they have to put on scuba diving gear and dive into the oil and the water. And by the way, people are lighter than oil, so there's no way you can swim in oil. If you fall into oil, you will drown if you're not wearing some sort of breathing apparatus. So they have this thing, and they discharge all at once and produce, for 1 nanosecond, the most power on the surface of the Earth of anything. It's a huge, well, frankly, explosion. And so here it's been caught in the act, and you see all this current running sideways and stuff. This is all the current that's not doing what it should. It should be going all the way down in here. So it represents like 0.1% of the current that didn't go somewhere. And the rest of it is going down here, and it's heating up a sample to 2 or 3 million degrees. We don't need 2 or 3 million degrees for the surface of our white dwarfs. We only need like 15,000 degrees. So we put our experiment a little bit farther away so it's cooler. And some of the data that we take as a result of that looks like this. So I apologize for the graph, but imagine this is red over here and this is blue, and these are the dark lines that you have. So we're actually able to measure how wide the lines are as a function of what their wavelength, what their color is. Now again, referencing my son, he's been in various daycares that were really cool and had science days and stuff. And I discovered a couple of years ago that he thought the word science meant explosion. Because all cool science stuff, the volcano blows up, the balloons blow up, firecrackers blow up. Well, and it turns out that in this particular case it's right, because when you cram 26 mega amps into a size like this, in 1 nanosecond, it blows up. So you're not really going to be able to see the blow up. I apologize for that because it's unsafe. But they put a camera in the room, this time with the lights on, so you don't see the sparks everywhere. You just see, in fact, you just see the motion of the equipment. You don't see anything else. But here it is. So it's finished charging up, and I've stood right outside the door to the reactor chamber when this happens. The 2 flashes of red light, there it is. So it's basically a seismic event. The whole building shakes. If you look out the window, this is Albuquerque and there's dust everywhere. You can see a wave of dust propagating because the earth is shaking. There's a nearby building that's missing some tiles near the roof because somehow the waves just focus right there and knock off tiles. So it's a really very impressive thing. They're doing great work at Sandia, and we're really lucky to be a part of it. So in the next, and we have 3 grad students working there who are going to be finishing this work in a year or 2. So anyway, we're going to know more about the masses of white dwarfs, and so we're going to know more about white dwarfs. White dwarfs are great clocks, great chronometers. We can learn about how much mass stars lose from white dwarfs, because if we know the sun started at about 1 and it winds up at about 0.56 solar masses, then it lost about 0.4544. I have to get my son to do the math for me. So we can learn about that, and we're doing laboratory astrophysics to connect astronomy and physics in the lab. And we'll know a little bit more in a couple of years, so stay tuned. Thanks, everyone.
All right, thank you.
We got a bunch.
All right, we're going to take some questions. I'm going to work top down, up in the top and the very back. Where's the closest white dwarf?
Where's the closest white dwarf to the Earth? That's a good question. I know a close one. You know the big bright star Sirius, which is like 8 or 9 light years away? It has a white dwarf orbiting it called Sirius B. So that's a very close one.
What's the distance?
About 8 or 9 light years.
We have a question on Twitter. So just to remind you, you can ask questions on Twitter. Just feel free to tweet us if you don't want to raise your hand. So the not-so-math Pedro Morales Almazan asked a question. What causes the brightness to oscillate?
Oh, that's a good question. Yeah. I do know, but it's hard to explain. The radiation, the light that's coming out of the white dwarf, gets selectively trapped and released at the surface. So it's kind of like a valve. Lots of things oscillate when you have something flowing through them, like if you have a sign and the wind's blowing, then you typically get the sign oscillating like this. Think of all the energy flowing out through the white dwarf. It gets dammed up and then released, and that's what makes it get brighter and dimmer.
All right. Okay. right there.
Yeah.
The young gentleman.
So I think, what about black holes? I'm sorry?
Black dwarf.
Black dwarfs. Oh, good question. Yeah, people say that when a white dwarf cools off all the way, it becomes a black dwarf, and that is totally true. But the reason I give the air quotes is because there hasn't been enough time in the universe for one to cool off that far yet. So, you know, eventually, maybe in 100 billion years.
All right, right here.
Cooling off to expanding into a red giant?
For the sun, it'll be about 9 billion years. But for a massive star like 10 solar masses, it'll only be like 30 million years. Oh, the actual expansion? No, probably more like 100 million years. Yeah, but still small compared to the life of the star.
All right, we're going to go over here.
Do the white dwarfs eventually become uniform internally, and is there a minimum temperature? The other question is, during the expansion phase, are there pressures that eject planetary bodies, or do they just continue in their orbits and rotation?
Yeah, good question. So white dwarfs do continue to cool off. The older they are, they will keep getting cooler. They're carbon and oxygen in the core, and that doesn't really change much as they cool off. But the hydrogen that they have forms a pure surface layer. You know how hydrogen rises? So it all bubbles up to the surface. So you get a little ocean of hydrogen, and below that a little ocean of helium. And the second question was...
As they expand, do they eject?
Are there pressures that push planets away, or do they just stay there?
Planets? Yeah, that's a great question. What happens to the planets when the stars lose mass? I am not an expert, but as the star loses mass, that's going to create a drag on the planets and cause them to fall in a little bit. But the mass of the star is going down as it loses mass, so it has less gravity to hold on to the planet. So it depends on the competition of those two things. And I think for our solar system, it might not. They might kind of balance. But for each star system, it's going to be different. Different things can win.
Okay, we're going to do two more. Lady right there. It was possible for two stars to collide to throw off the measurement with time that you're measuring. But
Oh, yes. Very good. Yeah, so if you had two white dwarfs that merged, that would mess up our measurement. But it would be a more massive white dwarf than normal, so we'd probably be able to figure that out. But that's a really good question.
all right, gentleman standing.
How do you measure those oscillations while at the same time it's spinning around?
Yeah, they rotate. The ones that pulsate, they rotate about once a day. And actually, we're able to model that at the same time we're modeling the pulsations. And so the pulsations actually tell us how fast they're rotating. But yeah, we do need to figure all that in.
Okay, one more from the regular up front who stayed with it.
So you didn't say anything about type 1A supernovas. My grandfather began accumulating a huge amount of gas from the result of type 1A.
They are pretty cool. I couldn't do everything in 15 minutes. But yes, if a white dwarf has a friend, orbiting it, and that friend dumps mass on the white dwarf, it could eventually get so massive that it would start to collapse and then explode in a type 1A supernovae. And those are the really important supernovae that tell us how far away distant galaxies are, or some galaxies are. And so that's how we figure out, that was the first evidence that the universe's expansion was accelerating, was the type 1A white dwarf supernovae.
All right, let's thank Stardust Necromancer one more time.
Thank you.